Hello everybody. In this video I'm going to talk about the factors affecting reaction rates. So chemical kinetics is really all about the rate at which a reaction occurs, so how fast a chemical reaction occurs. And reaction rate is a measure of the rate or speed of a chemical reaction, and it is determined by measuring the change in concentration of reactants and products over a certain amount of time. So if the concentration of products, say, is increasing very quickly, then that reaction would have a high reaction rate. Or if it's a very, very slow change in concentration, it's a slow reaction rate, right? But they figured that out, determined experimentally by measuring concentrations of reactants and products and how they change. And there are these factors that influence the rate. And really what happens is the way they affect the rate is by changing the frequency, the orientation, or the energy at which particles collide. So how often they collide, the amount of energy they collide with, or the orientation of the particles. Because remember, for reactions to occur, to be successful, they have to have the right amount the right amount of energy and the correct orientation. So there's 5 factors that affect the rate of reaction. One of them is the nature of the reactant, so how complex the structures are. The more complex the bonds that have to be broken and formed, and the orientation that's going to make it take longer. So it's kind of like putting together a puzzle, right? If you have what you consider a standard puzzle, you might be able to put that together very quickly. You're able to get the right orientation of those pieces. But then when you start getting into crazy looking puzzle pieces, it's going to take quite a lot longer to get them orientated the right way. It's the same kind of thing with that. Now, the state also has an impact. Homogeneous or homogeneous tends to be faster, right? So 2 liquids would usually react pretty quickly. And heterogeneous a lot of times is a little bit slower. So if a gas reacting with a solid, right, that might end up taking more time. And a big part of that, especially if a solid is concerned, is because of the surface area, right? It's only going to react on the surface. So the reaction would kind of have to work from the outside in kind of deal. The temperature, there's a rule of thumb, roughly generally every 10 degrees Celsius doubles the reaction rate. I mean, it's not going to be true for every reaction, but it's a ballpark figure. The concentration, remember, for reactions to occur, there has to be collisions between the particles. So if you can increase the concentration, you're going to increase the number of collisions, right? Remember, aqueous solutions, you can change concentration. Gases, you can change pressure. Solids and pure liquids, though, like water is considered a pure liquid, they cannot change concentration, right? You can add more to it, but you're just changing the amount, not the concentration. But the way you want to think about it is the higher the concentration, the more collisions, so the faster the reaction rate will be. And then surface area is another one. If you can increase the surface area, you can increase the frequency of collision. So like I was saying, this is especially true for heterogeneous systems, and especially if solids are present, right? Imagine having a solid that you can grind up into smaller pieces. You just increases the surface area greatly. So now that gas or liquid or whatever it is can react with more of the solid. And there could also be a catalyst. And remember, a catalyst does not get consumed in the reaction, and it speeds up the reaction by lowering the activation energy. And really what happens is it forms a different activated complex, right? So these are the reactants, this is the product, and in this case, the activated complex incorporates this catalyst, but then it breaks apart and you get that catalyst back. It is not used up. So for something to truly be a catalyst, it has to not get used up in the reaction. Inhibitors now, they actually decrease the rate of reaction by taking the place of a reactant or stopping the reaction. So it's kind of the opposite of a catalyst. And inhibitor you hear with like medical type stuff, right? There's inhibitors to block things from happening. Right, that's basically what's going on. Like this piece is supposed to fit in here, well, the inhibitor is blocking it. Right, so inhibitors, think about them as the opposite of catalysts. They slow down or stop the reaction. And remember, when there's a catalyst, it lowers the activation energy because that activated complex has a lower energy. It doesn't change the amount of energy associated with the reactants or products. That part stays the same. It just changes the size of this hump, essentially, is how you can think about it. That pathway has a lower activation energy when a catalyst is used, which makes the reaction go faster. It increases the rate of reaction.